this question. So it's a 1 out of 1,000 chance. And again, I think a lot of people think of 1 out of 1,000 is 1 out of 1,000, right? So how could it be anything other than they have a 1 out of 1,000 chance? Let's see what you guys thought. All right. Ooh, very nicely split. So out of 61 people, we are split into 25, 22, and 14. This is quite close, so I think I am going to open it up for another vote, but let me make two different ways you can think about it. So one way you can think about it is, the answer, the probability is 1 out of 1,000. So if the probability is 1 out of 1,000, then, of course it's going to be 1 out of 1,000. The population rate is 1 out of 1,000. We picked somebody from the population, should be 1 out of 1,000. So that would, if you believe that kind of way of thinking, then you would select this. They have a 1 out of 1,000 chance of having the test. The other way you can think about it is something like we just calculated in class that if you got a positive test result, like if the test comes back positive, the chance was 5%, I think we said, 1 out of 20 about. So if you get a positive test result, then the chance goes up from 1 out of 1,000 to all the way up to 1 out of 20. And we did all the gory details with the big tree and all of that stuff last class. And that was all perfectly correct. So you could kind of think of going to the doctor. When you go to the doctor, that is kind of like a really, kind of noisy test, right? Because the only people that would go to the doctor would be people who maybe have symptoms for it or are talking about it with their doctor. And so that's kind of like a crappy version of a medical test. It's just going to the doctor and talking to the doctor. And so if you believe that way of thinking, you would probably think it's somewhere between 1 out of 1,000 and 1 out of 20. Okay, but the question is, which of these ways of thinking is correct? They could both be correct. I will tell you, this one, they have a less than a 1 out of 1,000 chance. That one is definitely wrong. There is nothing going on here that would cause your probability to go down. Okay, so I'm going to send it out for a revote. This time, talk to your neighbors, see what their opinion is as well, and then we will reconvene in another 2 minutes. All right. Okay, it's open again. You can put in your updated answers. Even if you don't want to change your answer, you do have to put your answer in again. Okay, let's see how the revote went. Did people change their answers? And if so, in which direction? Last time it was pretty split. This time, we have a somewhat large majority on they have a greater than 1 out of 1,000 chance. And I think that is the correct answer as well. So I think this is the quote unquote Bayesian way of thinking about probability is when you have some unknown event, there are different pieces of information that can affect the probability of that event. And we saw a precise mathematical calculation for what happens with that test. So if it really is 1 out of 1,000, and you really get this mathematical test, you really get this medical test that has this 99% accuracy, then it went up to 1 out of 20. So let me write that down. Let's write this down. This is what we did last class. Okay, this is the wrong Blackboard. Okay, I want to click on this one. Say, this is from a while ago. Oh, this was counting stuff. Let's make a whole new one. That'll be fun. Okay. So last time, okay, we calculated the probability of have disease given test positive. That's what we calculated. And we worked it out. It took us a lot of work, but it was approximately 1 out of 20. 1 out of 20. And that was by starting with, we started with the ingredients of, there was a 1 out of 1,000 chance of having the disease. And we started with I think a 99% chance of the probability of test positive given you have the disease. And the reverse was also given, 98% chance of the probability you test negative given you don't have disease. Okay, and here I'm being like slightly informal by writing out words for these events. So have disease is the event you have the disease. Test positive is the event that you tested positive. And we took these ingredients and we combined them into a probability tree, and then we used that probability tree to calculate this 1 out of 20. And this is the so-called Bayes type question. Bayes type question. Why is it called Bayes? Well, Bayes was some guy. I think he was a reverend or something. He wasn't actually like a super hardcore mathematician, and I think people only discovered this work after he died in his notes. And it was all about flipping conditional probabilities. So flip the conditional probabilities. And what do I mean by flip? You'll notice the thing we wanted to calculate is the probability you have the disease given you test positive. That was what we didn't know. And we were given the reverse. We were given test positive given you have the disease, right? And combining all these calculations together, we were able to flip the probability. So that's the Bayes way of thinking. And there's a theorem called Bayes' theorem that lets you do it kind of more formulaically. I won't say exactly what it is, but there's something called Bayes' theorem. Bayes' theorem. Bayes' theorem basically takes what we did last class and it packages it up. Can also do this. And it's really an equivalent
Professor
thing.
Nika, you're leaving them in suspense.
Should I tell them? Should I tell them?
Go ahead and
The secret?
tell them.
Okay, all right. Let's tell them the secret. Okay, the probability of A given B, it's something, 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 times the probability of B given A. B given A. Okay, we got to figure out what is a something, something, because they're not equal. This is the thing. If you think they're equal, you're going to have a bad time, right? The probability you have the disease given you tested positive was only 1 out of 20, even though the reverse was 99%. But the thing that is true is you can multiply by a certain ratio, and I believe the ratio is like this. It's times the probability of A divided by the probability of B. It's either that or the reverse, and I can never remember which. So here's what we're going to do. We're going to prove it. Proof, PF in math class stands for proof. Let's prove it. And the proof is very simple. You write out the definition. So the left-hand side is the probability of A given B, which is the probability of A and B divided by the probability of B. That's very good. And the right-hand side is what? The probability of A divided by the probability of B times the probability of B given A. I can also write that as a definition. And this time, we divide by the probability of A. Okay, and here's where the magic happens. The right-hand side is constructed, so the probability of A cancels from the top and the bottom, and you're left with the right-hand side. So therefore, the left-hand side equals the right-hand side. We can do 2 lines. If you want to be really fancy, you do a little box. That means I'm done my proof. Okay, so that is the Bayes' theorem. So it says you can flip the probabilities if you can calculate the probability of each of the individual events, and you multiply by that ratio, that will let you do it. In the case that we did over here with the testing positive, it's actually a little bit annoying to use the formula, because you have to calculate the probability of B, and the probability of B is the probability you test positive. And unfortunately, there's two ways you can test positive. You can either test positive when you actually have the disease or when you don't. So we used a version, we split this up into two parts. So we did this actual formula, the probability of B given A, and then we divided here. The probability of B we wrote as the probability of B and A plus the probability of B and A complement, and we figured all these out. This is why I think it's better for very kind of the simple questions we're doing in this class, is to kind of know how to work it out. If you just kind of memorize the formula, I think it's easy to get mixed up on what you actually have to do. To me, the formula is a shortcut. Once you've understood this and have done 20 practice problems, then the shortcut kind of like packages that up for you. But that really is what we've been doing. Okay, any questions or comments about that so far? Maybe I'll talk a little bit about the warm-up in a second, but this is a good place to stop. For questions? Are those okay? Okay, so what is the Bayesian way of thinking? The Bayesian way of thinking is always think of probabilities as things that are updated as you have new information. So the probability you have the disease, if you're just a general person in the population, it's 1 out of 1,000. If you test positive for the test, then it goes up to 1 out of 20. But other things can move it up or down. So for example, if you have symptoms, that would move the probability up. So the probability that you have the disease given show some symptoms, that would go up, right? This would boost it up. This is larger than 1 out of 1,000, right? And then if you have enough symptoms that you go to the doctor, then maybe it's even higher. And then by the time the doctor actually says, okay, we should actually send the medical test out, then your probability is not 1 out of 1,000, it's something much larger, which means that when you actually get your positive test, the probability 1 out of 20 will also be larger. So the calculation we did was sort of assuming the background rate is 1 out of 1,000, but in real life, the background rate will change based on the information the doctor has. And this is in fact why doctors ask you questions like, do you have any symptoms? Do you have a family history of this disease? And this is also why doctors don't just give you every possible test all the time, right? They only give you tests for things that they think you are likely to have, because if they give you tests for things that you're unlikely to have, the test will not be very informative. It will only give things like 5% chance. So this is the Bayesian way of thinking, which maybe I'll summarize it as a quote. Update your probabilities based on new information. Or maybe constantly update your probabilities based on new information as it comes in. Okay, and the Bayes theorem tells you a sort of a quantitative way to do that, which is equivalent to the way we've been doing with cutting away things from your probability tree. Are you a Bayesian, Professor Humphrey, or are you? What's the opposite? I forget.
Former chair at Stats and Act Sci at Western, Ian McNeil, once said to me, every statistician would be a Bayesian if we just knew how to get the priors. So
okay.
often we can't.
So in other words, when you actually do statistics in real life, the hard thing is to know this 1 out of 1,000. So what is the probability to start with?
Yeah.
So the updating part, that part is actually okay. It's the what was the probability to begin with that is the hard part.
Prior probabilities are the real. There's cases where we have them, and other cases we know nothing about them.
Yeah. So
and that idea, the information that the doctor has coming in, it's going to depend on how good that information is. So, if they come in, I've been having headaches. Well, people get headaches for all kinds of different reasons. And maybe in this case, it's a very rare disease, like a brain cancer or something like this. But you don't automatically think brain cancer when you hear a person has a headache, right?
So given if you have the conditional probability that you have a headache, it is more likely you're dehydrated than you have brain cancer.
Yep.
Just because being dehydrated is a more likely thing.
It's a much more likely thing, yeah. So it's a very tricky thing for a doctor to diagnose a rare disease that doesn't have very obvious symptoms and a really good test. And then even if they have a really good test, if it came back with a positive diagnosis, what they like to have is further testing. And you may not even tell the person that, they may not even tell the patient at that time how that test came back until they get another test, because they know it's very difficult to diagnose rare diseases because there's a very good chance you're wrong with a lot of the tests. Yeah. There's another way of thinking about, so here's one, is to think of, we did urn problems before, 2 urns, and we said we're going to pick an urn at random, okay? 50-50 chance of picking each urn. But one of the urns has got 99 black balls and 1 white ball, and the other one has 99 white balls and, what did I say, 99 white balls and 1 black ball. And you're told that an urn was picked at random and then a ball was picked at random. And if you're told the color of the ball is black, do you still say the chance that it came from urn 1 was 0.5? Well, you've got this updated information because you knew it was much more likely to get a black ball from the urn that contained almost all black balls than from the urn that was almost all white balls. And you could work out that probability, update your probability that you took the black ball from each of the 2 urns. So we got a couple more urn questions for you. Illustrate a couple more things. What else have you got?
So yeah, the plan was to go back now and do the problem that was due on the homework on Friday in detail for people who missed that one. And also, we're going to show this formula in action and the other way to do it.
Okay.
So
actually, let me just finish off the end of that.
Yeah,
last
maybe there's
basic.
something else to say about this rare disease first.
Kind of just want to finish up the end, the very end of this one. And we have discussed this. So where am I? Where am I? Let me get me.
Hey, those were the numbers we did on the blackboard.
Yeah, those were the numbers. These are the numbers we did on. Oops. Yeah, don't do that to me. Don't do that to me. Just a second. Let me just see if I can get it. I don't want it there. It was in the right spot, and then it decided it was going to go somewhere else. Let's go back to there. That's what I want it to be. And let's see if I can get it to start at that particular spot. Yeah. So that was the end spot. We've discussed those numbers. And the really key thing to note is, Professor Nika has already stressed this, that the key idea is that, yes, there is a high probability of getting a positive diagnosis if the person has the disease. But when we consider the size of the population, the number of false positives simply swamps the number of true positives. And that's an important thing in the sense as we're discussing, is that's what makes it very difficult to diagnose rare diseases. And so when you hear that doctors have missed some diagnosis for some disease that is almost never seen, some of that would be related to the sense of probability. Okay. I had a couple more urn questions, but did you want to do that other one first?
Well, why don't we? Yeah, we have.
Oh my goodness! There's just so many things.
Why don't we let the students decide? We could have a little vote. Let's. So I guess here are the options.
Well, these are the boring questions, and they're kind of easy. And then, well,
there was the exciting urn problem.
And then there's the more. Oh, okay. You got a very exciting urn problem on the homework. Yes. Okay. We should do the exciting problem.
Okay, well, okay, let's.
Although
Now I want to see what this book is.
artificial insemination
I mean, that sounds exciting.
Artificial insemination is kind of interesting too. And
This
we
is-
are at an agriculture. I mean, we have our history as an agriculture college, which we're still very proud about. So we could do that one, but no, let's go back. I'll just put that one up. And then this one is just even more wicked. And then I have questions that get even into the more wicked things. But let's go to the homework
Let's do the
problem,
homework.
because that
Okay.
one's been done. Okay.
These ones will be good.
So
Okay,
hide
so
these ones.
we're gonna review some of the homework problems from the last homework, and there were 3 sort of tricky ones that were all kind of this
Let's
Bayes
take
thing
this one over here.
of answering conditional probability questions. And I think the 2 that are started with, one of them was the magic number. Is that what I called it? The magic
Yeah.
number.
Switch that on to
Oh,
your.
I have to
you gotta
turn it
move that.
on, or it doesn't do anything.
Both of them.
Very good. Thank you. Okay. The magic number, and this was the one where you flip a coin and roll a dice. Flip a coin and roll a dice. Okay. And it looks like this. I have it right here. So in a certain board game, you flip a coin and roll a dice. The probability you win the game is blank. And given that you won the game, then the probability that the original coin flip was tails is blank. And this second one is exactly this kind of Bayes thing, where the problem tells you basically straight up, if you flipped the coin and it was tails, then what would be your chance of winning? That's easy. But doing it in the reverse is what is being asked, and that is the Bayes theorem type thing. So that's one question. And the other one was this poor guy who was wrongfully imprisoned and had to escape prison. So that's one. And then there's the prisoner escape. And this is the same kind of one where the prisoner, like, he's got 4 roads to escape. So he can go out road 1, road 2, road 3, or road 4. And some of them are better for escaping the prison than others. So some of them are very likely to escape. And if you choose other ones, you're very unlikely to escape. And let me see if I can pull up that problem as well. I have to close this, and then I have to click on this one. Okay. So that is this one over here. 4 roads lead from the county jail. And again, part B says, if the prisoner succeeds, so they escaped, what is the probability they escaped by using road 1? So same kind of thing. And both of these were on the homework, and they were both, I think, the hardest questions of the homework. They were the ones that most people got wrong, and many people tried several times before they got them. So we'd like to go over at least one of them in class. Potentially both of them, but more likely one of them. But I will let you guys choose which one would you like to do. So we're going to see one of them now for the next 20 minutes. So there's magic number, or there's prisoner escape. You've seen both problems. Which one should we give a nice detailed solution for and talk about it in the context of Bayes' theorem? So those are your choices. Who would like to vote for magic number? Magic number. And who would like to vote for prisoner escape? Okay, lots more people on prisoner escape, I think. Prisoner escape is the winner. So let's do prisoner escape. And let's start by reading the question. So there's 4 roads. And again, your version of the problem would have had slightly different numbers. So some of the numbers are randomized every time you do it. By doing random numbers, it lets us give you unlimited attempts to do the problem. If there was only one set of problems, then you would know the answer, and then you wouldn't be able to try it again. But this way you can try it over and over again until you understand what's going on. Okay, so if road 1 is selected, you escape with probability 1/9. If road 2 is selected, it's 1/6. If road 3 is selected, it's 1/4. And then if road 4 is selected, it's 2/5. Let me sort of indicate these in my little picture. So road 1 is 1/9. Road 2 was, what was it, 1/6? I got to maybe do this. Okay. Road 2 is 1/6. Road 3 is 1/4. And this one is 2/5. Okay. So that's like very roughly recording the information given to us in the problem. And it says, hint, draw a probability tree. This is the only way to do the problem. So really, you really should think of these 4 options as splitting up like this. There's 4 roads, 1, 2, 3, 4. Okay, and we are going to choose one of these roads at random. So a prisoner has escaped from jail and selects a road uniformly at random. This is a funny word, which is used a lot, and maybe we didn't define it. So maybe this was a confusing moment for people. What does uniformly at random mean? Does that mean the prisoner was wearing a uniform when they left? No, it doesn't. Yeah, what do you think it means? Yes. So this is the thing. In sort of day-to-day life, you'll tell people pick at random, but at random could mean different probabilities. At random could mean road 1 is the most likely, and road 2 is less likely. But uniformly at random is like, no, I really mean really at random, where they're all equally likely. So this kind of idea that in regular life, random means just like equally likely, but in probability class, you have to specify equally likely, and uniformly is there. This is an important idea. This has rubbed off onto my wife. One time we were having a debate on which, she wanted to go to one restaurant, I wanted to go to a different restaurant, and I said, okay, why don't we pick at random? And she's like, okay, let's do the random distribution that is 100% my restaurant and 0% your restaurant. So she knew it wasn't uniformly, and that was clever enough that I let her win. So that was, she showed that she understood this idea. Okay, anyway, let's continue down this thing. So they're uniformly at random, so the first layer of the tree is 25% each. I'm gonna write 25% as 1/4. That's the uniformly, 1/4, 1/4, 1/4. And then each of the trees, they have these branches given by the probabilities over there. So let me do that in blue. 1/9, 8/9 to not escape. So this is escape. I'll say not escape, not NE. Is it you don't escape. Okay, this one splits, this one splits, and this one splits. 1/6 and 5/6 to escape or not. Let's write it like this, escape or not. And this one is 1/4 and 3/4 to escape or not. And 4 is 2/5, 3/5 to escape or not. So that's the probability tree. And setting it up, so what did we have to do? We had to unpackage the uniformly. We had to take all the probabilities, and we had to draw this big probability tree with 8 possible things that can happen, standing for escape or not, and which tree you're in. You could also organize it as a little table or a Venn diagram. So you could draw it a little bit like this. So you could have roads, roads 1, 2, 3, 4. Road 1, road 2, road 3, road 4. So this is my space of probabilities, is this big rectangle. And it's split into 4 events, road 1, road 2, road 3, road 4. And each of them is 1/4 of the space, so they're each 25%. And then they are further subdivided, right? They're further subdivided into escape and not in different amounts. So this is 1/9 to 8/9. And then this one is 1/6 to 5/6, or 1/4 to 3/4, or 2/5 to 3/5. And then you sort of have this blob on top over here that is the escape, and you have a different blob that is the not escape. So that's another equally good way of thinking about it. But it depends on your artistic abilities, which one you like better.
So Professor Nika, I got to
yes.
give you the gears about your diagram.
Yes.
Here.
Okay. Tell me what don't you like about my diagram?
I'm wondering about the space up here.
Yeah. There's nothing in there.
So I don't like that.
Okay. Let's try it. So I think let's
just a nice rectangle partitioned up.
We could either say there's nothing here, nothing out here, or you could maybe draw it even better. You could draw it like this. 1, 2, 3, 4. Now it really looks like there's nothing because they go right up against each other. And then you could split up these things. It would be something like 1/9, 1/6, 1/4, and 2/5. That's quite the large quarter I have over here. But you have to trust the numbers and not the artist. When you're as bad of an artist as me, you have figured out many years ago not to trust the artwork and to trust the numbers. But it's something like that. So that's another way to do it. And escape, again, is this combination. So maybe that's a little better than not escape, which is down here. Okay. Yeah. Was there also a comment? I saw a hand, maybe? No. Okay. Either way, these all represent the same thing. Okay. So that is the setup. If you know how to do the setup, I think you are most of the way to doing the question. That is the hard part. To me, that's the hardest part. Yeah, how many people got this far in the thing? Okay, yeah, great. Okay, and then it says, what is the probability the prisoner will succeed in escaping? What's the probability they will escape? So again, the picture makes it kind of obvious over here that there's 4 different ways it could happen. And up here, again, you would sort of have to count a little bit more and see, but it's still 4 ways. And so in this case, I think the answer is 1/9 plus 1/6 plus 1/4 plus 2/5. What do you guys think of that? There's a nice answer, whatever that works out to. Let's add it up. Okay, I guess we got to find a common denominator. 1/9 plus, maybe that's the hardest part of the question. Okay, so I go into 45ths. So 5 45ths plus. Okay, we got to include a power of 3 here as well. Oh, there is a power of 3. There's no power of 2. Okay, we got to go into 90ths. We're going to try again going to 90ths. How many 90ths? That's 10 90ths. Okay, that I can do. And then 6, I got to multiply by 15. 15 90ths plus this. Oh, that's also divide by 2. 22.5 90ths. All right, I'm doing a little sneak here. Times 4. That's right. Okay, good. And then 90ths. 9 groups of 10, 18, 36 90ths. All right. Someone tell me which ones I got wrong. Are those close? Yeah. Okay, good. So the addition is okay. The probability theory part is not okay. Is that the? Yes. Okay. Good. So let's do the addition first. Whatever this works out to be. 25, 40, 47.5 plus 36 out of 90, also known as 73.5 out of 90. All right, that's a fun probability. You could do it out of 180 if you don't like halves, or you're better at doing common denominators than me, but that's okay. So 73.5 out of 90, that is a probability, but as was pointed out on the far end over here, that is not the right answer. That is wrong. So something is 73.5 out of 90, but the something is not the answer to the question. So what did I forget to do? Yeah. Yeah, so it should all be multiplied by a quarter. So a quarter times all of this is the correct answer. A quarter times all of this. That is correct. 1/4. That is correct. And it's easy to forget that if you're looking at this picture and interpreting it wrong. So this picture makes it seem like the escape event, which is a combination of 4 events, is 1/9 plus 1/6 plus 1/4 plus 2/5, which is exactly what I did. But you have to remember that these fractions, 1/9 and 8/9, represent how much of this piece we are talking about. And each of these pieces is 1/4 wide. So this 1/9, that is not the area of that little square in the corner. 1/9 is the proportion of that square amongst the full column. So the whole area of this thing is 1/9 times 1/4. Everything is actually times a quarter, and that is coming from the 1/4s in the top. 1/4. So each of these pieces is 1/4 wide, and that's why you have to multiply by a quarter. That kind of calculation is easier to see in the probability tree. So in the probability tree, I have my quarters nicely labeled, and I probably would not have forgotten the quarters, whereas in the picture over here, I did forget the quarters. So very good. That is the probability to escape. Okay, this is the probability of escape. And again, we've sort of symbolically written it as a sum of 4 things. It's either you escape and you went out road 1, plus you escape and went out road 2, and so on. You escape out road 3, plus the probability you escape out road 4. Okay, it was a sum of 4 different things, and in each of them, you had to first go out the road, and then you had to escape. So it was a quarter times something in each of the cases. Okay, so that's the first part. Questions or comments about that first part? So the second part is the Bayes theory part. So given that you have escaped, what is the probability you escaped by road 1? So this is, the first thing you must do is interpret this if as a conditional probability. So it is the probability that we went out road 1, given we escaped equals question mark. That is what it says. And now that I have gotten that piece of information, I can make everything bigger. And you can see it's a Bayes theorem type question. The probability you go out road 1, given you escaped, that is hard. But the probability that you escape, given road 1, that was 1/9. We were told the reverse, we were told just in the problem. So if you say 1/9, you're mixing them up. So the sort of way we've been doing it before would be to say, let's highlight what we want. So we could find the highlighter, which is here. Okay. So this is escape and road 1. That's the thing we want, divided by the probability that we've escaped at all, which is a sum of 4 things. Those are the 4 things we did before. So we could write it like this, going all the way down. All the writing got bigger. Okay. It's the probability that you went out road 1 and escaped divided by the probability you escaped, which we've calculated. So 1 out of 9 times 1 out of 4 is the top. That's the top branch. And the probability you escaped we calculated before. That was the 1/4 times 73.5 out of 90, unless I made some adding mistakes. But that is that one. So that's the way we would sort of do it before, is we would take what we did before to calculate the probability of escape, and we would divide it by that sum. Let me highlight all those ways for extra clarity. Okay, you could escape that way, or this way, or this way, or that way, or this way. So the probability you escape is the orange branch divided by the sum of the 4 green branches. Fortunately, we did the sum of the 4 green branches already, and so we can just divide by the number we got before. That's the way we've been doing it before. You could also, now that we know Bayes' theorem, you could do it sort of another way, which is you could write something times the probability you escape given you took road 1. So the probability that you took road 1 given you escape is related to the reverse, and you have to multiply by this ratio, the probability you took road 1 divided by the probability you escape. And you will recognize these numbers. The probability you took road 1 is 1/4, and the probability you escape is this crazy number from part A. And then this probability was 1/9 that was given to us. So you can either do it the old way and get 1/9 times 1/4, or you can do it the new way and get 1/4 times 1/9. Those are both perfectly valid ways. So this is the Bayes theorem way. The Bayes theorem way, the probability of I given escape. Okay, and those are both perfectly good ways to do the problem. Mostly to show you that the Bayes theorem is the same as what we did before, but kind of in a packaged formula. Is there a question over here? Yeah. Yes, right, of course. So when you go to type in your final answer, you can cancel them out. Or you can leave them in. I think the computer, it will count anything equivalent as correct. I will say when we're grading your exam, if you have at least an intermediate step where you write it like this, it's easier for us to grade. We can see that you wrote down the right things. If you sort of cancel it without writing it down and you make a mistake, then we won't see that you actually had the right thing and made a mistake simplifying versus made a mistake with the probability. So it is nice to leave it like this and then cancel maybe in the next step. The 1/9 also cancels, right? There's a 1/9 and a 90, so you could probably simplify this a little bit more. All right. It occurs to me now, maybe the difficulty with this problem was how ugly this number, 73.5 out of 90 was. I didn't realize it would come out so disgusting, but that is life, I guess. Any questions or comments about the prisoners escaping?
I will add a comment. In this problem, they took the prisoner took one of the 4 roads with equal probability, 1 out of 4, and that kind of simplifies things a little bit, not as much as you might think, but it does simplify it a little bit. But it would have been very easy to give different probabilities for each of the roads, right?
Yes, actually, this is a good point. Like the mistake I made would have been much worse if they were not all 1/4, right?
Right.
So I added up these 4 numbers, and I did all this work adding it up, and then fortunately we could just throw a 1/4 on the front because they were all 1/4. If they were all different, right, you would just have to start over and multiply each of them by a different number. And we could have could just specify different probabilities, or it could give you a thing that the prisoner threw
pair of dice, and if it came out the sum was 3 or less, they took the first road, and if it was 4, 5, or 6, took the second road, and maybe a 7 or 8 was the third road, and otherwise it was the fourth road. So the point is you can add degrees of complexity to these questions, but if you think them out very methodically, you know how to do it all. You do know how to do it all, right? So be very methodical. You can go back to the diagram where Professor Nika partitioned that sample space into quarters. But again, it doesn't have to be quarters, again, with different probabilities, and everything else is still just done the same way. Anyhow, I'm going to put up the extra questions, and then maybe Friday I might take up 1 or 2 of those.
Yeah. And don't forget, you also have homework on Venn diagrams and counting problems also due on Friday.
Yes.
Okay. All right. See everyone on Friday.